So I'd like to add my thanks to Danny for the opportunity to be here today, and to you for attending this session, and just speak a little bit about work that we have ongoing in areas of upgrading water. Our laboratory specializes in membrane technologies, both for water purification as well as gas separation. There are many opportunities for upgrading water. I just mentioned a couple here because they've been discussed in some of the earlier presentations. One is in the area of desalination, the other in organics or particulate removal. And we'll start just a little bit with the discussion of the desalination part, at least the way it plays into the use of membranes for desalination. And so if you think about it, for a long time, people have been involved in desalinating water. You can certainly do that by boiling water. It comes at enormous energy costs, as indicated here, with some engineering. And you can bring that energy cost down tremendously by recovering a lot of the energy that's used in the evaporation. Modern reverse osmosis or desalination costs are down around 3 to 4 kilowatt hours per cubic meter. So it is, for seawater desalination, this is the least expensive way to remove salt from water. And this slide shows a summary of costs today. The reverse osmosis is down near the bottom. We're still several times higher than the limits that are imposed by thermodynamics, and that represents an opportunity for us to continue to improve membranes as well as processes. This technology is already used and has been for many years in large-scale facilities. This is showing a bank of membranes at the Ashkelon desalination plant in Israel. For some time, this was among the largest plants in the world, making close to 90 million gallons of fresh water, potable water a day from seawater. And recently, the largest system in the world has also come online in Israel, making 165 million gallons per day of potable water from seawater. The previous speaker touched briefly on salinity scales, and so I won't belabor this point except to turn your attention to the second line of the units of grams per liter, fresh water being about 0.5, brackish water between 0.5 and 30, and ultimately what I will call brine is being well above seawater, above 50 grams per liter. And so if you put that onto a map of desalination technologies, what you find is that at the very lowest levels of salt in water, typically in the range of area where people are doing ultra-pure water manufacture, technologies like ion exchange and electrodialysis are used. Basically, you take the salt out of the water. In the mid-range concentration, which is near brackish water and seawater concentrations, reverse osmosis is used. Here, you basically remove the water from the salt water, so the separation goes the other way around. And finally, at very high salt concentrations, reverse osmosis due to osmotic pressure limitations becomes infeasible, and the thermal techniques are the least expensive. You may have already heard or know that there is now recognized a strong connection between water and energy. We just talked a little bit about the energy required to make water, and clean water, of course, is required to produce energy. It turns out that the largest category of water use in the U.S. is at thermoelectric power stations, and so we use an enormous amount of water to actually generate electricity, and this is part of the basis of the so-called Water-Energy Nexus. Economic growth is tied to water usage. As economic growth increases, the use of electricity increases and the use of water increases. So we need water in order to grow the economy because we need energy to grow the economy. To look a little bit broader at this, and particularly something closer to home, here in Texas as well as a number of places, we've seen a tremendous development in the form of shale gas through hydraulic fracturing and particularly horizontal drilling. It's unlocked enormous energy reserves. Some of the impacts of that are shown in these articles or headlines from the vernacular press. People like the CEO of General Electric saying that this may be one of the biggest productivity drivers in our lifetime. companies like Dow and others along the Texas Gulf Coast are expanding enormously to take advantage of the low-cost hydrocarbons that are being unleashed by this technology. Those who are interested in CO2 concentration in the atmosphere are also finding reason to celebrate, because as coal-fired power plants make a switch to natural gas, the CO2 emissions by the U.S. have gone down. In fact, they've gone down by more than any other nation on the planet in the past 7 or 8 years. However, you need a lot of water in order to extract shale gas. The fracturing requires millions of gallons per well, and it's often needed in places where we don't have a lot of water. And on the order of 20 or so percent, depending on the well, but a fair amount of that water actually comes back as so-called flowback water that's contaminated not only with oil and grease, but a number of other contaminants you find in the ground and also in the fracturing fluids. And so there's been talk about cleaning that water for various beneficial uses. One of the problems with cleaning dirty water with membranes, a perennial problem, is so-called fouling. If you look at the cartoon on the left and you imagine that you're using a filter, if you will, to filter contaminants out of water, one of the problems is that the contaminants can accumulate on the surface of the filter and clog it, and this leads to a reduction in flux, as shown on the right. With time in membranes, this necessitates expensive cleaning, or you have to put in additional membranes to account for the fact that you can't operate at the clean membrane flux. We and others have been looking at technologies to alter the surface properties of membranes to try and control fouling. One of the approaches that we have worked on is based around so-called polydopamine. This is a route that was initially discovered by Phil Messersmith's group at the University of Illinois, looking at an entirely different set of problems, that of underwater adhesives. It turns out that under mild conditions, the dopamine molecule undergoes oxidation to produce a substance known as polydopamine that deposits in nanometer thick layers on virtually any surface it comes into contact with. Importantly for us, it renders those surfaces hydrophilic, and so this gives us a very facile way through aqueous chemistry to make virtually any surface, including membrane surfaces, hydrophilic. This often makes the membranes more resistant to fouling by hydrophobic foulants like oil droplets. There's still a lot of debate about the structure of the material that's actually put down on the surface. I won't belabor that here, but we've worked closely with colleagues in our chemistry department as well as in other institutions around the world to try and better understand the structure of these materials. I'll just describe briefly some of the results from applying this type of surface treatment to membranes, and that will be described in the form of so-called constant flux fouling experiments. We do these types of experiments because this is the way membranes are often operated in the field. You have a given amount of water to process with a given area of membranes, and you operate those membranes at a pressure difference across them so that they process the amount of water that's needed. And so we flow dirty water past the membrane module that's shown in the middle of this slide, and we control the flux or flow rate of water through that membrane. And as the membrane fouls, the pressure difference required to keep the water flowing through the membrane goes up. And so that transmembrane pressure, or TMP, increases with time. And that's what we'll take as a metric of fouling in the next couple of slides. I'll show you time as the volume of water produced by the membrane per unit area. And in these types of experiments, that's directly proportional to time. So this is showing results for a membrane used in purifying an oily model, oily wastewater system. The unmodified membrane shows significantly higher transmembrane pressure difference than either of the membranes that are surface modified. And the energy cost associated with this separation is directly proportional to that transmembrane pressure difference. We go to even higher fluxes, you see an even greater improvement in the resistance to fouling of the modified membranes. And so a question is, these are laboratory tests, does that translate to the field? And so in order to do that, we'll have first to look at the fracking water cycle and focusing on the purification of flowback water, that is water that comes back after water's been injected into the well. There has been talk for some time about treating this water for beneficial use, such as reusing it in oil and gas applications, or perhaps even in other uses. The pilot test that we conducted is in the Barnett Shale area that's shown here. And this is a picture of a mobile frackwater purification unit that was built by a startup company that was spun out of the University of Texas based upon this research. The company's called Advanced Hydro. And like the previous speaker, I'm now required to tell you that both the University of Texas and I have a financial interest in this company. So take whatever else I say with that in mind. And so in our pilot test, we ran ultrafiltration membranes to remove particulates ahead of reverse osmosis or RO membranes to desalinate the water. We ran coated or modified membranes in parallel with unmodified membranes. I'll only show a sampling of the results here that show the water flow at a given pressure drop through the membranes. The modified membranes are shown in red, and we're getting more water per unit pressure drop through them all throughout this pilot test. There's a lot of variability because the incoming water to this sort of process varies enormously over time. We go through several very straightforward cleaning steps. Those are the hot water clean and so-called CIP cleaning steps. We can also plot the results in a performance metric that is basically how much more energy efficient is the modified membranes relative to the unmodified ones. And by the end of this short test, we were approximately a factor of 2 better by that metric. Now, this technology has not taken off commercially in Texas because it turns out that like in any business, you have to always be aware of what the competition is, and competition in this case is shown in red here. It's transporting that frack water to a disposal well and burying it. And our technology is not competitive with a hole in the ground, at least not today. And so our focus has shifted to treating helping generate fresh water for this process. It turns out that, as you saw from the previous slide, you need an enormous amount of fresh water for this process, often in areas where there's not a lot of water. And this brings into a third actor into the water-energy nexus, and that is that water for hydraulic fracturing is actually displacing food production. And so these are headlines just from the vernacular press over the last couple years talking about the competition between food and oil and gas exploration for water, and the food is not winning. And so what I'll show you next are basically poor versions of the slides you just saw. And this is some of the shale plays in Texas. A couple of them are shown in the dotted circles in the Eagle Ford and the Permian Basin. And this is a map of underground water availability showing the availability of brine. There's a brackish water brine aquifer that is present in these areas. And so currently we are drilling down into that brackish water aquifer. It's below the conventional water table, and bringing up brackish water, treating that water to generate fresh water again in a mobile scenario on site for water for fracking, and then the brine can be used also in killing wells once it's brought to appropriate saline. So this is a zero discharge type operation. This is a schematic of the first 250,000 gallon per day system that went online a couple of weeks ago in Snyder, Texas. So we're hoping that there'll be more of these to come. This is also generated mobile or portable small-scale desalination systems that are now under evaluation at the U.S. Bureau of Reclamation facility in Alamogordo for rural desalination, so small-scale desalination. And so we have, starting with basic chemistry in this area, generated structures that can be used to improve the fouling performance of membranes of oily wastewater. We've had the good fortune to work with folks in the commercial sector to help us reduce that to practice, and then be able to apply that in the oil and gas sector. And so the surface modification of these membranes can mitigate fouling in some cases. We've been able to translate that to the field. There's a lot of fundamental research that we're still looking at in the lab to try and make this more effective. And those of you who know anything about the way research works in the university know that I don't do any of the work. I come and spend my time with Danny talking about the problems and others from time to time. But it's the kids in the lab that do all the work, and so I certainly want to acknowledge them. And I want to thank you for your time today. And when we get to the discussion, be very happy to answer any questions.